Alright, welcome everybody to the Chapter 2 lecture video on Sections 1 and 2. I'll try to keep it short. One of the things I want you to make sure you're doing is writing down where you might have questions. If you have struggles with how things should be going, please do email me. Best way to contact me right now is via email. I've been pretty good about responding as quickly as I possibly can. You can also send me a message on Canvas or on Discord if you have me there, and so on and so forth. Alright, so let's get started. Here we're going to look at some different information in Section 1 of Chapter 2 on terminology. We're going to focus a lot on terminology here, and this is kind of like what we call the fundamentals. We're going to build on these, and we're going to learn about things like velocity and acceleration. We're going to take everything in one dimension, and we're going to take it into two dimensions in the next chapter, but there's a lot of stuff that's going to build on concepts that we're going to talk about in this section, so please make sure you pay very close attention, especially in this chapter and in Chapter 3, because the fundamentals are going to be something that come back to get you every time. All right, so first things first, let's talk about position. So when we define position in physics, one of the things we want to do is we want to define that position in time. So in other words, if I wanted to say that, at time 0, when I started my stopwatch, I was standing right in front of my house, then I am at what I would define as a position. A lot of times we will say that the starting position of an object is at 0 in order to simplify problems as much as humanly possible. So if I say I started in front of my house and I walked to the store that was 2 kilometers away, then what I'm saying is I moved from my 0 position to a position 2 kilometers away from that initial starting position. And while I'm measuring that position, I can measure time from start to finish. And remember that time always starts at 0 in physics. In other words, we start our problems at the very beginning of whatever motion is being discussed. From there, we can talk about the term displacement. So when we change our position from our initial spot to a new spot, whether it be to the right, to the left, up, down, north, south, east, west, what we're doing is we are now inserting this idea of displacement. Displacement and distance are not the same. In fact, displacement is referred to as the change in position from the starting point. So, if I start in front of my house, I go to the store, and then I come back to my house, my displacement is 0 because I measured it from that initial spot. So, our initial reference frame, we're going to talk about reference frames a lot, but the reference frame that we start with is going to be the thing that we measure changes in accordance with. So in this particular case, my reference frame is the starting position in front of my house. If I move away from that reference frame, I have displaced myself. And if I stop my movement away from where I started, then I have a displacement that can be measured, also known as change in position. And we'll see some examples here in a second, but just understand that when we talk about displacement, we're saying change in position from a 0 spot. And here's where we're going to insert some mathematical variables. We're going to use a delta to indicate change. We're going to use things like xf, and this should be a subscript, and x naught to indicate initial and final positions. A lot of times in physics, what we'll do is instead of even putting the f in there, we'll just use x and x naught to indicate initial, and then x to indicate wherever you stop. Now, delta means change in, so when we subtract final minus initial, that's how we get our delta change in position. And we can do this in x, we can do this in y, we can do delta t, we can do delta anything. And we'll see delta come back a lot. The SI unit for displacement in physics is going to be meters, but we can also use units that have prefixes on them. So we could use kilometers, we could use millimeters, we could use megameters, which I personally don't use, but you will see a few times, especially when we talk about planetary scales. Okay? Think planetary when you hear the term mega, think a car's distance when you hear kilometers, think millimeters when you think more like molecules or small objects moving. And then we obviously use meters to indicate like people, or like a lot of times we'll use remote controlled cars or battery operated cars. So small objects that move on their own. Remember that displacement, again, is from the 0 point. And because of that, displacement is actually going to have both direction and magnitude, which makes it a vector quantity. We'll talk about vector quantities more in the future, but for now, just understand that if we say it's a vector, it means it has both direction and magnitude. Now, in the case of physics, direction can be anything from literal direction, go right, go straight, go backwards. Direction can be the cardinal directions, north, south, east, west, northwest, southwest, southeast, etc., etc. Direction can be an angle, so theta. Anything that's not even, it can come out to be 23 degrees, it can be 14.273 degrees, it can be any angle. Just understand that that is considered a direction if you're given an angle on which something applies. We can even just make direction a positive or a negative sign. These are some of the more common examples of how direction is indicated in physics. Magnitude is just going to be exactly what you think. It's a scalar quantity. So in other words, if I say the car traveled 25 meters, that's just giving you quantity. I'm not telling you which direction the car went. If I say the car went 25 meters north, now I've given you a displacement because I've told you where it's gone from where it started. Okay, so displacement versus distance is one of the more common, like initial kind of I don't get it type things. Here we have an example on the left and on the right. Over here we have a teacher, I hope, moving from left to right 2 meters from her initial position being x naught. They labeled it at 1.5 meters, but we could just as easily measure it at 0 meters, and then we could find that her x final could be measured at 2 meters to make our math a little bit easier. In this case, you could do the same math, not so hard. You do final minus initial, and you get that displacement of 2 meters from the initial. In this case, she moved to the right. In physics, when something moves right, it's positive. When something moves left, it has a negative sign, okay? Up here we have an example of a passenger on an airplane moves from their seat to the back of the plane, from their initial position to their final position. Since they're moving to the left, we've labeled this as a negative sign. It just means that it's just the 0 point, wherever we put that 0 point at the beginning of a problem, that's how we define everything from there on, okay? So one of the other things that we want to talk about is how is this different from distance? If I say the car travels from your house to school, then from school to Starbucks, and then from Starbucks back to your house, if I ask you what the total displacement is, your answer should be 0. It didn't end up any different from where it started. The other question I can ask you is, what is the total distance that you traveled? And you would have to add up the distances between each point to figure that out. And here we have an example that Professor, I do this all the time, can pace all over the place, maybe walking a total of 150 meters or, a mile during a lecture, and then you might still only end up right back at the front of the room where you started, which means really your displacement is 0 or close to 0. All right, so that's all for section 1. It's displacement, distance, what is kinematics? Kinematics is what we're studying, motion in objects. From there, one of the things that we also addressed here was assign direction, assign a 0 point in order to assign direction. Displacement is going to be the difference, and distance is going to be total length. We also talked about SI units and the fact that displacement is a vector quantity. All right, moving on to section 2. All right, so section 2 deals with how do we set up problems to be successful? Excuse me while I drink my pumpkin spice latte. In this particular section, we're going to work with vectors, scalars, and coordinate systems. So a vector, like we just said, is going to be magnitude and direction. Any quantity that has a magnitude and a direction, aka a plus or a minus sign is the simplest version, is going to be a vector quantity. We're going to graphically represent these with arrows, because if you think about it, an arrow, I apologize, if you think about it, an arrow, no matter how you draw it, has magnitude, aka size, and it has direction. So I can say this arrow is pointing up, this arrow is pointing northeast. I can draw one that points down here. I can draw one that points straight right. I can draw a very, very tiny one. I can draw very large ones, and so on and so forth. The arrow is going to be our easiest graphically representable version of a vector quantity because it can point in any direction. We can describe direction, like we said, in various ways, including the degree, we can talk about the cardinal directions, north, south, east, west. We can talk about left, right. We can do positive and negative, and so on and so forth. Here, the difference between a vector and a scalar is going to be that the scalar has no direction. So think temperatures, how many calories are in the bag of chips you eat, how fast a car is going. Think instantaneous velocity. That car is going 90 miles an hour. If you tell me that car is going 90 miles an hour, A, I'm going to be like, whoa, way too fast. And B, I'm going to say which direction. Because if you just tell me 90 miles an hour, I don't know where it is, I don't know where it's going, and I don't know what it's doing. A person's height is going to be a scalar because it doesn't change and it has no direction. You can't say my height is 1.8 meters up. Like, obviously your height is 1.8 meters up. That's kind of indicated in height. But the thing is that this is a scalar because I'm not needing to give direction in order to understand. Distances are also scalar quantities unless you tell me which direction. Which brings us to the basic how we're going to use coordinate systems. We are going to use the standard 4-quadrant coordinate system in physics. We're going to say that if it's got a positive x and y, that it's up here in quadrant 1, and if I get it wrong, I'm sorry, don't be mad. We are going to use this standard quadrant scale. I think that's right. If you have a negative x and a positive y, you're above the axes, but you're in quadrant 2, and so on and so forth. With motion, if we go to the right, like we said, we're going to say positive. If we go to the left, we're going to say negative. If we go up, we're going to say positive, and if we go down, we're going to say negative. So for all of our physics problems in this class, we are going to start right here. Always. Okay? We're going to start in one place, and we're going to analyze motion from that location. For this particular purpose, as long as we're all on the same page that up is positive, down is negative, left is negative, right is positive, we can get problems on the same page, right? Like whatever answer I get is going to be the same one as you get. All right, that brings us to the end of section 2. That's all I wanted to talk about today. We're going to work more on sections 3 and 4 in the near future, but for now I'd like you to work on those homework problems I assigned over these sections. Those are going to be due by the end of the day today, and it's Wednesday. So yeah, I miss you all. See you later.